Hello. In this video, we're going to be talking about the polar and exponential representations of complex numbers. So before we do that, we're going to have to review the rectangular or Cartesian representation of complex numbers. So given a complex number z, we can write it in rectangular coordinates as a plus bi, or a plus ib. And we can actually plot this on a plane just by imagining a rectangle with width a and height b. Or we can think of it as a point with the x-coordinate a and the I-coordinate, or the y-coordinate as we're used to, of b. Now to convert from rectangular to polar coordinates, or from polar to rectangular coordinates, we have to find an angle and we have to find the length of that line created from the origin to our complex number. So we're going to have to use some basic trigonometry. So we can represent a polar coordinate by its angle and its length. And the angle is going to be the angle counterclockwise from the positive x-axis to the line formed from the origin to the point itself. And we'll just draw a quick picture to kind of get an idea of what actually is meant by that. And the length of the complex number is just going to be the length of that line from the origin to the point. Now we may remember from basic trig that the sine of theta is going to be the opposite side over the hypotenuse. So the length of the opposite side is b, and the hypotenuse is always going to be the length of z, our complex number. Similarly, our cosine is adjacent over hypotenuse, so it's going to be a over the length of z. So this tells us that if we're given something in polar coordinates, we're given a length and an angle, we can actually just solve for a and b and put it right into rectangular coordinates. So a is going to be the length of z cosine theta, and the length of z sine theta is going to be our b. Now, since we're in the plane, we can also define length as we normally would in the plane. So the length of our line from the origin to the point is just going to be the square root of a squared plus b squared. So let's just write down exactly what it means to convert from polar to rectangular. And then from rectangular to polar, it's going to be a little trickier, but not too much more difficult. So to convert from rectangular to polar, we already have our length. It's the square root of a squared plus b squared. So we just need to find our angle theta. So we can remember from trigonometry that the tangent of theta is going to be equal to the opposite side over the adjacent side. So in this case, b over a. So if we want to find the angle, we can just take the arctangent of both sides. So theta is actually equal to the arctangent of b over a. And now we have our r and our theta, and so we have it in polar coordinates. The nice thing about rectangular coordinates is that we can add them and subtract them very easily, but multiplying them is really kind of convoluted and tricky. That's kind of the opposite case when it comes to polar coordinates. So in polar coordinates, adding is kind of difficult because we'd have to look at them as vectors and then draw, an arrow tip to tail to subtract, and it's really complicated. But multiplying them is a lot easier, and that tells us that division's also pretty easy. So to multiply two polar representations of complex numbers, what we do is if we have r with an angle of theta and another complex number, say s with an angle of phi, to multiply them, we're just going to multiply r and s, and then we're going to add the angles phi and theta. So r angle theta times s angle phi is rs angle phi plus theta. And to divide them, we're just going to divide the coefficients, or the lengths, and then we're going to subtract the angles. So r over s angle of phi of theta minus phi. Algebraically, this kind of looks like how we would multiply a constant times an exponential function. So this is actually the natural link between polar coordinates and exponential form. So we can convert r with an angle of theta to r to the ei theta in the complex number system. And we can see that this is a direct analog to what we just stated with polar multiplication and division. The next question naturally becomes then, how do we represent these in different coordinate systems? Well, polar to exponential is fairly easy. We already have r, and we already have theta. So if we have our exponential form as r e to the I theta, and we have our polar form of r angle theta, we can just substitute the r in polar for the r in the exponential, and the theta in polar for the theta in the exponential, or vice versa, and it's really easy to convert from one to the other. Converting from exponential to and from rectangular, though, is a little trickier, and the best way that I think to do this conversion is just to convert to polar first and then go into the exponential form. If we're converting from exponential to rectangular, we already have r and we already have theta, so we can just use the polar conversions to convert to rectangular form. So let's look at two examples. So first, let's convert 3 plus I4 to exponential. So the first step is to go polar, and I originally wrote 3 plus I, but it makes the calculation of the length a little tricky, so I just made it 3 plus I4. So to go polar, what we're going to have to do is we're going to have to look at the length, and we're going to have to find an angle. So to find the length, we can either use the Pythagorean theorem to find the length of the hypotenuse, or we can know that it's Pythagorean triple of a 3, 4, 5 right triangle. So this tells us that the length is actually 5. Now to find theta, what we're going to have to do is we're just going to have to take the arctangent of 4 over 3, the I coordinate over the real coordinate. And when we do this, it's not a nice number. It's about 53.3 degrees, if I remember correctly. But that's about 0.93 radians. So once we have our r and we have our theta, oh there it is, it's 53.13 degrees. But since we're in math and we're not doing anything that would warrant degrees, let's just stay away from that and use radians. So 3 plus I4 is going to be r with an angle of theta, so 5 with an angle of 0.93. And then from our polar representation, it's really easy to go exponential because we can just replace it, and it's going to be 5e to the 0.93i. Okay, and next we're just going to show how to convert from an exponential to rectangular form. So let's convert 2e to the I pi over 2 to rectangular form. So we know that r is the thing in front of the e, so that's a 2, and theta is the thing next to the I, so that's pi over 2. So we just are going to use our conversions. A is r cosine theta, and b is r sine theta. So That tells us that a is 2 cosine of pi over 2, and that's going to be 2 times 0, because cosine of pi over 2 is 0, which is just 0. On the b coordinate, or the imaginary component, it's going to be 2 times the sine of pi over 2, which is 2 times 1, which is going to be 2. So this tells us that our rectangular coordinate conversion gives us 2i. Thank you for watching.